Regional Group and the Conference Coordinator. I am beyond happy to welcome you today to Neuroplasticity and Education, Strengthening the Connection. We will have our official start at 8:30, but right now I am very privileged to welcome Dr. Justin Davis, and he will be speaking to you about brain basics, really to set the stage for today, to give us all a great overview on the amazing power of the brain and what we can do to really control it and to be able to change and strengthen it. But before I do that, I just wanted to go through a few little housekeeping items. One, of course, even though it's early, let's put our phones on vibrate. I know many of us are moms and dads and we have small kids, so of course we don't want to turn our phones off, but vibrate would be wonderful. Also, for those of you who enjoyed tweeting, we will be doing some live tweeting today. The hashtag is NeuroEd2013, so feel free. We won't think you're being rude if you're checking your phone. But for now, I'd like to tell you a little bit more about Dr. Justin Davis. As the Scientific Director and Product Manager at Noggins Brain Fitness, Dr. Justin Davis is committed to helping individuals find the information and products necessary to maximize their brain's potential. His goal is to combine his expert knowledge in the field of human neuroscience and love of teaching to motivate others to adopt a healthy brain lifestyle and make brain fitness part of their everyday routine. Dr. Davis loves inspiring people to challenge themselves with new brain exercises, activities, and products to improve key brain functions. He believes that brain fitness is as important as physical fitness in order to achieve peak performance at work, in the classroom, and at home. Dr. Davis was awarded a doctoral research award from the Canadian Institute for Health Research. He is a member of the International Society for Gait and Posture Research, and the Society for Neuroscience and the Canadian Association for Neuroscience. So without further ado, it's my great pleasure to welcome Dr. Justin Davis.
Thank you, Sandra. I am beyond happy to be here as well today. Thank you very much. It's really an honor for me to be here speaking among such a fabulous panel. I hope everyone here today is extremely excited because you're going to hear it literally straight from the horse's mouth. There's a fantastic lineup of world-renowned researchers today, and you're in store for a very brainy day. And what we're going to do today is we are going to rewind the tape a little bit and get straight down to the brain basics. So for those of us who don't have a PhD in neuroscience, sometimes some of the more basic questions about the brain are nice to have answered before we get started. So as we get going here, I'm also going to let you know, I fancy myself as having a PhD in keeping it real as much as a PhD in neuroscience. So if you have questions, now is your time, all right? There is no question that is too stupid. There is no question that goes unanswered. Ask them. You can interrupt me at any point in time if you have one. Where are the washrooms? That is a great question to get us started. Through the lobby, sir, and just down to the left there. Can't miss them. Good question. Need to know. All right. So getting started then with the brain basics. It's a complicated topic. So starting from the very beginning, there it is. There's a picture of the human brain. Well, it's a cartoon sketch actually taken from Gray's Anatomy. And what I'm going to do now is I'm going to turn it over to you with a question to test our basic knowledge of the brain. So if you were to take a guess, in pounds, how much would you think the human brain actually weighs? 4 pounds? 3 pounds? 10? 8 pounds? 7? 3 to 4 pounds. All right? 3 to 4 pounds. So if you take that and put it into context, right now you are listening to the voice of a 200-pound individual. So when you think about it, 3 to 4 pounds is really only about 1 to 2% of our total body mass. The human brain is not that big. All right? What makes it so powerful are the neurons inside. And when you look at this picture here, you may think to yourself, wow, this is a fantastic microscopic image of neurons. It's not. It's actually a hand-drawn sketch that was drawn in 1905 by a gentleman named Santiago Ramon y Cajal, the godfather of neuroscience, literally. And it's this image here that has framed our understanding of how neurons are wired up. So when you look at this sketch, how many neurons do you think there would be in the average human brain? Let's get a couple guesses. How many? Really shout them out. I'm a little bit deaf up here. 4 million? Billions? Trillions? Roughly about 100 billion neurons, all right? Sounds like a large number, but put that 100 billion into context. Last year around this time when Facebook went public, they were valued at about $104 billion. The United States government bailed out the auto industry to the tune of $600 billion. 100 billion neurons isn't really that many. And that's part of where that old myth, you only use 10 to 15% of your brain power, or part of your brain, comes from. So looking at these neurons, you might notice they have branches. They're making connections with other neurons. So each of those 100 billion neurons, if you were to take a guess, how many connections would you think they're making on average, given neuron? These questions get harder. No guesses? 5? Trillions? Actually, individual neurons on average make about 5 to 10,000 connections or synapses per neuron, on average. Some neurons, like the ones in your cerebellum, they're going to be making hundreds of thousands of connections. Some neurons, like the motor neurons that are going from your motor cortex down to your toes, those ones are going to be making about 5 or 10 connections. So there really is a lot of variability, but on average, your neurons are making about 5 to 10,000 connections per neuron. So when you take 100 billion and multiply it by 5 to 10,000, now you are dealing with that incomprehensibly large number. It's up there in the quadrillions. And that's where the information processing power of our brain comes from. So, getting back to the brain basics. When you look at this picture that was hand-drawn by Ramon y Cajal, you may notice that in between the neurons, there's a lot of empty space. And we used to think that that empty space was just unimportant tissue, not of any use to the brain. And that's where that myth came from. We only use 10 to 15% of our brain. But what we've learned is that empty space isn't really empty space at all. There's a very important tissue inside your brain in addition to the neurons. It's called the glia, G-L-I-A, the glia. And you can think of the glia as the network infrastructure that supports the neurons doing all the important communicating that they do. So if the neurons are the nuts and bolts, the glia is the network infrastructure there to support them doing all the work that they do. And what's interesting about the glia is that it's a really fatty tissue. So if you were to take a guess of what percentage of your entire brain matter is fat, literally F-A-T, the total percentage of your brain matter that's fat, take a guess. What would you think it is? 98? Any other guesses? A little more overboard there. 80? 85? It's about 60% fat. It's about 60% fat. And I had an interesting question already this morning when I was out having breakfast about, talk about the effects of alcohol on the brain. So you can do a fun science experiment for teachers. You can do this in the classroom or you can do it at home. Take a little bit of butter and rub it between your fingers, or have your students rub it between their fingers. Get a sense of what that feels like. Then take a little bit of isopropyl alcohol, or if you happen to have any vodka in the classroom, you can use that. And then mix that in with the butter and get a sense of what that feels like. And then remember that the human brain is 60% fat. You're going to have a pretty good understanding of how alcohol impacts the brain. So that's just an aside. So here's what we know. We know it's 3 to 4 pounds. We know there's about 100 billion neurons that are on average making 5 to 10,000 synapses per. It's 60% fat. And one of the last things we can measure about the brain is how much energy it uses. So think about your breakfast that you've just had this morning. You're digesting it. It's being broken down into metabolic energy. What percentage of your total daily energy intake do you think goes to the brain? 74? I love your guesses. They're good. That's a little high. What was yours, ma'am? 25? Bang on. It's about 20 to 25% of your total daily energy intake. But put it again into context. The human brain, 1 to 2% of your total body mass, consuming 25% of your daily energy intake. It's a phenomenally energy-consuming organ. It really does take a lot of gasoline to keep that thing running. So, Those are the brain basics. This is what we can measure. But in the last few years, we've really come to understand this concept of neuroplasticity and how our brain can adapt from the moment we're born until the moment we die. And just as a shout out, I want to let everybody in the room know that neuroplasticity is really a Canadian discovery. So Donald Oldingheb, I know, he was working alongside a gentleman named Wilder Penfeld. You remember him from the Canadian Heritage videos we all watched when we were kids. I Smell Burnt Toast, remember that one, where he was doing the work on the woman with epilepsy? So he, Wilder Penfeld, and D.O. Hebb, they were the ones who coined that phrase, neurons that fire together, wire together. They were really good at taking little miniature electrodes, stimulating neurons, and measuring how much their potentials changed over time. And you know what? They were right. Neurons that fire together do wire together. But fast forward to the year 2000, year 2005, and we've learned that that term neurons that fire together, wire together, it's really not that simple. There is a little bit more going on inside our brains with respect to neuroplasticity. And when you think about the brain and you think about neuroplasticity as an umbrella term that covers a whole host of different processes that are allowing our brains to adapt from the moment we're born until the moment we die. So starting out at the very beginning. How many parents are there in the audience right now? All right, quite a few parents. I'm not a parent yet, but I was once an infant. And, I've seen a lot of infants. And I can tell you that most infants I know can't really walk, can't talk, don't have their own personalities, can't form long-term memories, abstract thoughts and reasoning, all the stuff that we adults do. And part of the reason why is because when babies are born, they're really born with all the neurons they're ever going to need. The problem is their neurons haven't been wired up or shaped by experience in any way, shape, or form. And as parents and teachers know, it does not take long to get from baby brain to teenage brain. And teenage brain definitely has a personality of its own, can walk, talk, form abstract memories, do all sorts of things. And of course, what's surprising for people is how we get from infant brain through teenage brain through to developed adult brain. It is through a pruning process, all right? And this is a very counterintuitive thing to think about, that during development and during adolescence, we're actually pruning back our synapses. So the analogy I use is simple. You can think of it like a rose bush. We need to prune those neurons to make sure they flourish and grow to reach their fullest potential. Or you can think of it in terms of efficiency. So the developing brain is wired to find the most efficient way to communicate. And you can think of neuron A and neuron B. So we're going to figure out how we're going to wire these guys up. And when the baby's born, there are many different connections between these neurons. And what happens is, if you imagine neuron A as being a city, Vancouver for example, and neuron B being another city, Toronto, when those neurons send their first signal to one another, the way they do it is they send out multiple signals at once. And one of those signals is going to catch the inefficient route. It's going to go from Vancouver up to Prince George, make a connection in Calgary, make a connection in Regina, and finally make that connection in Toronto. Took the long route. And of course, one of those signals is going to catch the direct route. It's going to make that direct connection from Vancouver to Toronto. And when that happens, the baby brain says, aha, this is the most efficient way for me to send that signal from neuron A to neuron B. So what I'm going to do is I'm going to prune back those inefficient stops along the way. So that's the only way I send that message. So counterintuitive, a developmental pruning process. And of course, neural development is very different than physical development. We reach our maximum height around 18 or 19 years of age, but our brains don't stop developing until we reach our late 20s. So the neurodevelopmental process goes far beyond our physical developmental process. And then development ends. And what begins? That's right, aging. And it's happening to everyone in this room. We're aging. We're losing neurons. We're losing synapses through the aging process. It's a fact. And of course, this changes the shape and structure of our brain. So think about pruning and the loss of synapses as one contributing mechanism to the neuroplastic nature of our brain. But it's not all bad news. Because contrary to popular belief, we do grow new synapses. So when I went to school, I was told, look, kid, you're going to be born with all the brain cells you're ever going to have, and you're just going to booze them and drink them and do drugs and bang your head against the boards in hockey, and it's a slow downward spiral to the end. Not the case. We do know that we grow new neurons. However, the popular media has jumped on the growth of new neurons and really exaggerated it to a large extent. So I really want to make sure that everybody understands it's not as though you lose a neuron, you grow a replacement neuron. And you're not growing them everywhere in your brain. You're only growing them in 2 areas, and one of which is the hippocampus. So by a show of hands, who's ever heard of the hippocampus before? All right, we have a pretty well-educated crowd coming in today. All right, so the hippocampus, as you already know, is very important for the formation of memories, in particular, spatial memories, so where we're going and how we're getting around. So it's kind of intuitive to think that, hey, in this part of my brain, the hippocampus, where I'm forming new memories, I'm also growing new neurons through this process called neurogenesis. All right, so neurogenesis you can think of as neuron, genesis, chapter 1 of the Bible, new growth. All right, so we are growing new neurons through that process of neurogenesis. And of course, if you look at this individual picture of a neuron, what would you say it looks like? Tree. Yeah, it's not rocket science, it's neuroscience. It's not lost on neuroscientists that neurons, in fact, do look a lot like a tree. And down there at the bottom, at the bulb or the trunk of the tree, that's the cell body. That's the part of the neuron that makes the decision about whether or not it's going to send signals out there to all of the other neurons in its network. And it does that based on information it receives from the dendrites. So the dendrites are out there, they're the branches, and those little yellow flecks, those are the synapses. This neuron's been stained to highlight those synapses, or the points of contact that are made between neurons. So when you look at this neuron over a period of time, as short as 24 hours, 48 hours, you can observe that a neuron, just like a tree, has the capacity to grow new branches, sprout new leaves, and go from being a thin, wispy palm tree of a neuron to a dense oak tree of a neuron. All right? So when you think about the brain and you think about neurons, and we've heard that expression that the brain is really a lot like a muscle. Yeah, kind of. The brain is more like a bush, all right? Full of neurons that are sprouting branches. And it's really an important process to understand that it's not like a muscle, it's like a tree. And it's our responsibility to fertilize that bush or that tree to optimize and maximize the number of synapses we're creating. So the time frame from this experiment is 48 hours. So I'll explain to you the trick that was used in this experiment. So an important compound that you're going to learn about today is called brain-derived neurotrophic factor, BDNF for short. And Dr. Rady is going to be talking a lot about this compound today. And you can think of it literally as the body's natural fertilizer for our neurons. So in this experiment, what they did was they bathed that neuron in brain-derived neurotrophic factor, and that's what literally promotes the growth of those new branches and those new synapses. And that's over a shorter period of 48 hours. Good question. All right. So back to this term neuroplasticity. Think of it as an umbrella term, all right? Yes, neurons that fire together wire together, but there are a lot of different processes that are contributing to the changing shape and structure and adaptive nature of our brain. Namely, the pruning of our neurons through the developmental process, and of course, the loss of neurons that occurs with aging. The growth of new neurons through that process of neurogenesis, and of course, the ever-changing way in which they are wired up through that process of synaptogenesis. So the synapse is the fundamental point of contact between neurons. Every time we learn something new synapse. Every time we have an emotion, that's represented by a synapse in our brain. A memory represented by a synapse. And over the course of our entire life, we're constantly forming new ones, breaking old ones, and strengthening ones that are important. And that's really going to be the theme of today's entire session. So getting back to how things really got started. So 2005, Fast forward from Donald Hebb understanding that neurons that fire together wire together. Who really cares? We didn't really start to understand how this impacted learning until around 2005. So, does anybody have a guess for what you're looking at right now? A map of Saskatchewan. No, the city planners in Saskatchewan did a much better job than the city planners of this city. But you're right, it is a map. Any other guesses? It is a European city. We're getting warmer. It is indeed London, England. London, England. So by a show of hands, has anybody ever been to London, England before? Yeah. As you can tell, tricky place to navigate. No straight streets. They didn't come up with a nice numbering system that we have here in North America. So as a consequence, one of the best ways for us tourists to get around the city of London is in a taxi cab. And taxi cabs in London are I gotta say, the most extreme example of learning and neuroplasticity in action. If it took me 6 years at UBC to get through my master's program and my PhD on top of 4 years of undergrad, you'll be surprised to know that to go from being a wannabe cab driver in London to a fully licensed cab driver is about a 5-year process. That's how long it takes to become a licensed cab driver. You have to pass a test known as the knowledge. And to pass the knowledge, you have to be able to plot the shortest distance between any 2 points in the city and name every landmark or point of interest you're going to pass along the way. It's a phenomenally difficult exam. People take about 12 attempts to actually pass the knowledge. And because of that reason, researchers at the University College in London became very interested in the hippocampus of these cab drivers. All right? So the hippocampus, we already know it's very important for memory, but in particular, it's our spatial memory. So if I were to, close my eyes, spin myself around, take a few steps back, I know that the edge of the platform is right there because I have a spatial map in my hippocampus that I've laid out of where we are, so I know where downtown is, everything. That's my hippocampus that creates that. So naturally, these researchers were interested in the hippocampus of these cab drivers. And sure enough, they found that on average, the hippocampus of a cab driver is significantly larger than that of everyday people. And of course, there's a correlation. So if you compare the size of an individual cab driver's hippocampus to the years of experience they have on the road, there's a relationship whereby those cab drivers who have been on the road longer and have more experience have a larger hippocampal volume than those that are new to the job. And of course, this was one of those first studies to hit the popular media. And it was all out there. All of a sudden, you can grow a larger brain. It was the first time it really hit the airwaves. But I hope in here we have a couple of skeptics, because there should be some questions that come about from this study. Namely, is it possible that these cab drivers were born with a larger hippocampus, thereby predisposing them to do well on the knowledge? And of course, I've shown you a correlation, not necessarily a cause and effect relationship here, folks. But rest assured, we do know that there is a cause and effect relationship. So in addition to cab drivers, another fascinating study that came out around the same time in the early 2000s looked at jugglers. And we learned that if I were to take half this room right now, put you over there, and I'm just going to leave you all by yourselves for 3 months, nothing's going to happen. In the other half of the room, you're going to come with me for 3 months, and we're going to learn how to juggle. So every day we're going to go through juggling exercises. So 3 months, every day, learning how to juggle, learning how to juggle. At the end of that 3-month period, if we use MRI technologies, we can actually take a look at the density of synapses in the region of our brain that's responsible for coordinating our movements. And sure enough, those of us who have learned how to juggle are going to have a denser area of synapses in that part of our brain than those that didn't learn how to juggle. What's more is 3 months later, after we go through juggling training, that increase in synapse density is going to go away. It's a transient effect. So we really do know that there is a cause and effect relationship between learning and the growth of new synapses. And it's gone on to be further demonstrated in those of us who are learning a new language, picking up a musical instrument for the first time. Any type of new learning and acquisition of new knowledge requires a synapse to be formed inside our brain. So, conclusive, it's out there. Learn, grow synapses. But of course, what I'm here to talk about today, beyond the basics of the science, is what do you do to create an environment that promotes neuroplasticity? How do you go about optimizing your brain health so that you can create an environment that will proliferate and foster the growth of new synapses? So with that being said, I'm going to turn it back over to the audience. Single most important thing you can do for your brain to promote neuroplasticity. What do you think it is? It is exercise. Indeed, it is physical exercise. So with that being said, I'm a big proponent of live the science. So put down your pens and papers and literally get on your feet for a moment. We're actually going to get involved in living the science today. Robbie Buchanan, I'm talking to you in the back row. All right? So, on your feet. So a little jogging, up and down. You have a big day of learning ahead of you, everyone, today, I'm telling you. Now, arms up in the air. Arms up in the air. Punches. Oh, I punched that. Okay, good. Now, everybody back down on your feet. Or on your butts. Good. All right. So, hopefully with that little bit of exercise, you should be feeling it. I hope a little bit of heart rate pumping. So, now that you know the brain basics and the fact that your brain consumes 25% of your daily energy intake, I hope it makes sense to you why exercise is at the top of the list. The way energy gets to our brain is our heart and lungs physically pump that stuff up to our brain. If you are going to get the energy that your brain requires, you have to have a healthy heart and lungs to pump that stuff up there. So, number one reason. The other thing we know about exercise is that if you are a long-time exerciser, you've exercised over the course of your entire life, you're going to have a reduced risk of suffering a stroke. You're going to have a reduced risk of suffering from dementia, specifically Alzheimer's. All right? So exercise, very, very important for the brain. I'm out of breath from my exercising. Switching to water. Well, that is a good question. So what type of exercise is the best kind? Yes, cardio is important, but there's all sorts of different exercises that are also going to present new challenges to the brain. Think ballroom dancing, all right? Think learning how to skate. Think any type of exercise that's really going to challenge you to coordinate your movements in new ways you've never coordinated them before. Again, new synapse needs to be formed, plus the added benefit of the cardiovascular fitness. All right? Good question. Yes, ma'am. Blood. Blood is the delivery mechanism for energy. So in order to make sure we're able to get that blood up to our brain, healthy heart and lungs is literally the pumping mechanism that gets it up there. So keep a healthy heart and lungs so you can deliver blood to the brain. So that's number one. Yes, ma'am. Please do. Pruning, yes. So it doesn't really begin and get going until adolescence is when there will be a little bit of pruning. So during the third trimester of the pregnancy is when the neurons really start to proliferate. And that'll happen through infancy and through early childhood. And the proliferation process will peak and it'll come down a little bit. And then that developmental pruning process starts. Good question. Yes, ma'am. Okay, good question. I didn't say it. Don't worry, there's not a neuroanatomy test at the end of this. It's called the subventricular zone. So there's a region in our brain, we actually have holes inside the dead center of our brain called the ventricles that produce the cerebral spinal fluid, and that's the second area of the brain where we've found that we're growing new neurons. And that's just two thus far. Maybe there's other areas. We don't know. We just haven't found them yet. The point I'm trying to make is we know that they're not growing everywhere. They're growing in specific regions. Good question. Yes, ma'am. Pardon me? Indeed, you do have to keep practicing. You do have to continue to learn new things. Back to that point about neurons that fire together, wire together, the more firing you get through more practice, the stronger the connection you're going to make is going to be. Not necessarily. In some cases, yes, but in some cases, no. Yes, sir.
Children sitting in a classroom, how often and how long do you recommend the exercise?
60 minutes a day, every day. That's not me. That's the Canadian, I forget which association it is, but kids should be getting 60 minutes of exercise every day.
But on an interval basis during the day within the classroom.
Dr. Rady's going to tell you a very interesting story today about the 0 hour program that was launched in Naperville, Illinois. And what he determined and what that study showed was first thing in the morning, so that's what we're doing here with our little exercise this morning, is really the time to get out there and get that exercise going. But really, any time you can get some exercise into the schedule is great. So the thing about exercise, I'm going to take more questions at the end. I'm just going to get through the first exercise one here first. So the other thing we know about exercise, in addition to helping us get a healthy heart and lungs, it's also releasing that brain-derived neurotrophic factor. When you engage in exercise, if I were to pull your blood, by that I mean put a needle in and take blood out, you can look for different hormones. And after exercise, there's a spike in that brain-derived neurotrophic factor. From other experiments that we can't do in humans, but we do in animals, so if you take a little laboratory rat, put him in a cage all by himself, no running wheel, no exercise, take another laboratory rat, put him on that running wheel every day, and then do what neuroscientists do best, which is cut their heads open and look inside, you'll notice that the rat that exercised actually grows more new neurons through that process of neurogenesis than the rat that doesn't. Physical exercise is a fantastic way to promote the growth and proliferation of neurons. Can't stress that enough. Were there any more questions about exercise before we move on to number 2? Yes, ma'am. The transfer effect. The transfer effect, yeah. So the question was, if I, develop a neuron or a new connection within a network that's going to make me a good ballroom dancer, is that going to necessarily make me smarter at math? And that's a very good question. And it's actively under investigation. But what we found out is that, yes, there are indeed transfer effects. The more neurons that you have connected with one another, the better and stronger your networks are going to be for a lot of reasons, okay? Good question. All right. So moving on. Number 2 on the list. So if exercise is at the top of the list, what is the second most important thing you have to do to promote positive neuroplasticity and brain health? Oh, I think I heard it. Sleep, nutrition, proper nutrition. So getting back to that point, 25% of your daily energy intake. If you're a teacher and you wonder why 2:30, 3 o'clock in the afternoon rolls around and you got a bunch of squirrely kids who can't concentrate, can't think, and can't really behave themselves, oftentimes it has to do with the fact they haven't had enough energy and basic nutrition, all right? And the one point that I want to make on that topic of the brain consuming 25% of our daily energy intake is think about white sugar, all right? Refined white sugar. I know I'm preaching to the converted at this point, but literally, a diet that's rich in refined white sugar, it's kind of like trying to, fuel a 747 by burning matches. A really quick, easy to burn type of energy, not a dense energy form like our ancient grains and all of the great complex carbohydrates. So try and keep that to a minimum. So the other thing about nutrition that should become relevant to you now that you know your brain's 60% fat is why every time you turn on the news, you're hearing something new about the importance of omega-3 fatty acids in your diet. So the thing about that brain fat that lives inside your brain, it's very different than the fat that lives on the outside of your body, all right? It is a dense lipid cholesterol, and you need those omega-3 fatty acids. They are the building blocks of all that healthy brain fat, and you have to get it from dietary sources. It's not as though you can eat a box of Dunkin' Donuts or Tim Hortons donuts and metamorphosize those trans fats into omega-3s. Doesn't work like that. Got to get them from those dietary sources, which is basically your Mediterranean diet. So everything you've seen on TV about getting sources of sustainably caught cold water fish, everything you've seen about eating lots of almonds, nuts, chia seeds, uncooked olive oils, all those sorts of things are a really important thing to get into the regular diet. Great. So, exercise. Oh, yes, sir. So the fish oil supplements is a good question. And I hate to disappoint everybody, but the science has come back to show that, hey, they're not necessarily bad for you, but there hasn't really been a demonstrated effectiveness of fish oil supplements for improving cognitive health and reducing dementia risk in older adults, or really having an effect on heart health either. What we found is that the bioavailability of omega-3 fatty acids in our food sources is a better way to get that. Good question. All right, so we have physical fitness, we have nutrition. Third on the list, whoa, 5 minutes. Stress management. Stress management. And I say the word stress management for a very important reason, because stress is one of those things where we've come to learn a little bit of stress is good for the brain. You have to experience it. So for anybody who's had a pop quiz, anybody who's ever been pulled over by the cops, anybody who's had, a fire in their living room and they've had to get their kids out of the top floor, and you've had that acute stress response, very important that you have that response. That fight or flight response is important. The problem is when it gets stuck in the on position, when you begin to experience chronic stress. We've learned that in high doses and in high concentrations, when those stress hormones stay in the bloodstream, not good for the brain. Shrinks and atrophies animal brains and is actually toxic to neurons in a petri dish. So stress management, very important that you find ways to do that. And you're going to hear a fabulous talk from Dr. Rick Hansen and Dr. Gabor Mate about ways to promote mindfulness to manage stress in the classroom. So look forward to that. Next on the list, socialization. Socialization. And for those of us with older adult parents, this is an aside, two of the biggest risk factors for developing dementia in later life, social isolation and loneliness. But for those of us in the classroom, this socialization conversation is a poignant one. And to be honest, the jury is still out on the effect of cell phones, technology, social media on the social development of kids. We haven't had that technology long enough to know. But we do know this, that as much as we use our brains for the heavy lifting of the math, the science, and the languages, we also use our brains when we're reading each other's facial expressions, laughing at each other's jokes, looking each other in the eye. And it is very important to get that stimulation during the developmental process. Long time ago, there was a product that made it to market called the Baby Einstein DVD series, Brainy Baby series. Put the DVD in, plunk the kid in front of the TV, and through osmosis, you're going to learn your shapes, numbers, and alphabet. It was actually found that those kids who were on the Brainy Baby program were slower to reach developmental milestones, namely their first words, than kids who weren't on the Brainy Baby program. The only way you can expedite those early developmental years and get kids to their first words earlier has been reading to them. So hugging them, cuddling them, giving them the social interaction that they need, because it's important for developing those networks within the brain. Socialization, critically important. As is diverse forms of mental stimulation. So that's what I'm talking about. Be a lifelong learner. Pick up a new instrument for the first time. Learn a new language. Play chess and learn the rules that you've never learned before. And really, it's all about novel and complex challenge. Anything that's new. And a lot of people like to talk about, doing crossword puzzles. And yes, indeed, crossword puzzles are fun and they're great. But a lot of the times, when you get really good at doing crossword puzzles, there's no longer that new challenge. And once you've learned something, memorize the entire crossword puzzle dictionary, you don't need to form a new synapse, all right? That's time for you to realize you need to reach out there, expand your learning database, and learn something new. Seek out novel and complex ways of stimulating the brain. And that is how you promote neuroplasticity, the 5 pillars of brain health. So my big mantra is brain health first, brain fitness second. And I think there's a few more minutes for questions before we get kicked off for today. So if you have any outstanding questions that you're nervous about today, don't hesitate to ask them. Really shout it out from the back there.
Do we understand the physical mechanism for the pruning? Like what happens when the synapse gets there and the first one comes back? What makes that prune? What happens in the brain? Does that make sense?
Not 100%.
Right.
Right.
How does it get rid of how does it
the inefficient stops along the way during the pruning process? That's a good question. And to be honest, if I gave you an answer for that, I'd be making it up right now. Those are the types of questions that are still actively being pursued in research labs around the world. We know that there's this pruning process, but understanding the signaling mechanisms to get those synapses to break apart, that's what the next generation is going to be figuring out. So, a big part of what I do is try and encourage kids to get out there and do some research, get the bug, and really do some science to answer those questions. It's a good one because we don't know. Right here in the front row. Yes. Oh, yes, ma'am, you with the green shirt. Yeah. The way to stimulate the production of BDNF. Exercise, exercise, exercise. All right, that's how you secrete that stuff. Yes, ma'am. Games like Lumosity. Fantastic. So when I talk about, brain health first, brain fitness second, you can play all those brain games you want, but if you're never going for a run and you're hooked on a diet of Doritos, are you really helping your brain? But if you are making exercise part of your regular routine, if you are sticking to the 5 pillars, doing working memory training is a fantastic thing to do. Barbara Arrowsmith Young is going to talk more about the benefits of specific cognitive training today, so I don't want to steal too much of her thunder. But yes, it can work. But you got to create the right environment in the brain to promote neuroplasticity. I think I got time for one last question. Yes, ma'am.
You said that when you juggle, the 3 months of juggling, and then you lose the skill, what happens to the taxi drivers who've been doing it for 20 years? What's the difference? How do you keep...
Why did you ask me a question I'm not going to be able to answer right at the end? Nobody knows. So the thing about the taxi cab drivers is they did the study and they looked at them during that time, but after they've retired, researchers are no longer interested in them. We didn't look at them, so we don't know. But what we've learned it's called the cognitive reserve hypothesis. If you're interested in learning more about it, read up on nuns, yes, Roman Catholic nuns, and you'll learn a little bit about the benefits of building synapses for building a healthier brain for the long run. So with that being said, we have a very tight timeline to stick to today. If you have more questions, because there aren't going to be a lot of questions today, don't hesitate to email them to me at justin@noggins.com. Or you can literally Twitter them to me at Dr. Noggins, and we'll try and make sure that we get those points taken up during the panel discussion at the end of the day today. So thank you very much.